My dear students, today we'll perform an practical based on the Hall effect. Okay. So let's try to understand first of all what is Hall effect. तो हम आज एक प्रैक्टिकल करने जा रहे हैं, हॉल इफेक्ट पे बेस्ड है। तो हमें ये देखना होगा कि हॉल इफेक्ट होता क्या है, राइट? व्हाट इज अ हॉल इफेक्ट? वेरी सिंपल। ये आपके पास सेमीकंडक्टर भी हो सकता है, मेटल भी हो सकता है, एन टाइप सेमीकंडक्टर भी हो सकता है, पी टाइप भी हो सकता है। So this may be a conductor, mean a metal, maybe a semiconductor, maybe n-type or maybe p-type. हमने क्या करना है कि एक करंट पास करना है लेंथ वाइज, लेंथ के अलॉन्ग, और ये स्क्वायर शेप का भी हो सकता है, नो प्रॉब्लम. We'll pass a current. Here in the figure it is lengthwise. And simultaneously we apply a magnetic field perpendicular to the direction of electric current. तो हमने एक perpendicular magnetic field लगाई है current की. तो we know very well about the Fleming left hand rule. लेफ्ट हैंड में क्या होता है कि ये फिंगर, फोर फिंगर, ये डायरेक्ट कर रही है मैग्नेटिक फील्ड के अलोंग, मिडल फिंगर ये पॉइंट कर रही है करंट की डायरेक्शन, और थंब शो करेगा फोर्स की डायरेक्शन. ओके, फोर फिंगर पॉइंटिंग टुवर्ड्स मैग्नेटिक फील्ड, middle finger pointing towards the flow of electric current, and thumb will show the direction of the force. Let I consider this is p-type semiconductor. That mean current mean the movement of the hole. They are going from left end to the right end because they will exert a force, because thumb shows the force. That means force starts accumulating here over this face and left behind the negative charge. So accumulation of positive and negative charge mean appearance of electric field as well as the voltages. And this process stops because magnetic field continuously tries to pull the positive hole along this side. But the process stops. You know why? You know why it stops? At some moment, magnetic force which trying to pull the positive charge over this face becomes equal with the electric force. You know, electric force is, electric field is positive to negative. Okay, when this electric force, because there is a tendency of the electric force to pull the positive particle along this side. Magnetic force tendency is to pull the positive hole along this side. When the two forces becomes balanced, the accumulation process stops. And at that time, whatever the voltage which appears established, that is called the Hall voltage. And electric field is the Hall field. Okay, this is what the Hall effect. Now what about the definition? Very simple. Magnetic field is applied to current in perpendicular direction. Then what happens? A potential difference or voltage or transverse electric field is created across the conductor. Okay, This phenomena is called Hall effect. Remember, field is perpendicular to current. Then a potential difference is created. Now just note, this is a semiconductor chip, N-type. Okay. Now this point, now very important here, green lead is connected to semiconductor at this end, and second green lead is connected to the semiconductor, at here. Okay, and we'll measure the voltage between this point and this point. And here the red lead is connected. Here the red lead is connected. Between the green leads, the current will be passed, and across the red leads we will measure the Hall voltage. So this is our semiconductor chip. It is very clear here. Just look, this one is the semiconductor chip. And back side is this one. Okay, to the back side, here it is a green lead, green wire, the green wire, and here it is red wire and red wire, 0.58 mm thick semiconductor chip, N-type germanium crystal. This is our electromagnet, This electromagnet will produce a magnetic field. Okay, when current is passed through the coils. So this we'll measure the field with the help of this probe. This probe is used to measure the field which is produced between the gap of the two poles. So probe is placed between the two pole pieces. This is a supply, electromagnetic power supply. With the help of this supply, we'll give current to electromagnet. These are the connections, positive, negative, DC supply. DC current will be passed to the electromagnet, and current will be adjusted through this knob, and the current it is in ampere. So the probe which measures the field between the two pole pieces is connected here. This is a probe is connected here. So when this knob, it is at this side, it is ready to measure the field which is in kilogauss. Now there is no field because no current is passing. Now I am increasing the current slowly, like 0.51 ampere. So magnetic field starts. Magnetic field is now created between the two pole pieces. It is in kilogauss, remember. Kilo is 1000. So field is, current is increasing continuously. Thereby, magnetic field is also increasing continuously. And this variation is linear. current is increasing. Just look, magnetic field is also increasing likewise. So now the current is 3.59 ampere and field is 0.12 kilogauss. So field is continuously increasing with the help of the current. Maximum current is 5.53 ampere, which can be passed through the coil. Now we plot a graph between the current which was in ampere, DC current, and field which is produced or created between the two pole pieces. It is in kilogauss and it is increasing with the current. And the graph is plotted here. Along this side, I have taken the current in ampere. Along this side, I have taken the field which is produced in the kilogauss. So graph is exactly a straight line, and the equation of the line is also given. The straight line equation, the exactly data points, they are fitted in the line. What is the use of the graph? The use of the graph is if you are having the value of the current which is given to electromagnet, like current which is given to electromagnet is 3 ampere, then what will be the field? We can have an idea. So if this is the current which is passed, what is field? So we can have the magnetic field if the current is known, which is given to the electromagnet. Now we have connected the green leads of the semiconductor probe. It is connected, look, to the above two terminals. They are for the, the current, another current. There are two types of current. One is passed to the electromagnet, which was from this supply. Now from this supply will pass a very small current in milliampere. So here the green leads are used for passing the current to the semiconductor chip. Okay. Remember, green leads connected above for the current, and other two red leads, they are connected below. They are used to measure the Hall voltage, which will be established when the current is passed. Okay. Now we put the chip between the two pole pieces here, in perpendicular direction to the current. So chip is placed between the two pole pieces. It is very clear. It should not touch with any pole. It should be exactly in between the two pole pieces. Now what we will do? We will measure current passed to the chip in milliampere, and side by side, because this knob is now in for current. After having the value of current, we'll note down what is the voltage which is established, Hall voltage. So Hall voltage is 0.67 millivolt. Now current is 1.83 milliampere. Voltage is 1.62 millivolt. Current is 2.52 milliampere. Voltage is 2.21 millivolt. Current is 3.9 milliampere. Voltage is 3.38 millivolt. So there is some problem here in the digital view. So be careful. You take your data. This is rough data. 5.14 milliampere. Now voltage is 4.39 millivolts. So you go on having the data between the current passed to the semiconductor chip and likewise the Hall voltage. Now 6.23 millivolt, 9.86 milliampere, 7.87 millivolt. So there is some problem in digital view of the milliampere and millivolt, but you should take your data with your instruments. So this is 8.77 millivolt. So one thing remember, during this experiment, the current which was passed to the electromagnet is constant. It was constant. The current passed to the electromagnet was constant. No change. And when the current is constant to electromagnet, means magnetic field remain constant. What we are varying, the current passing to the semiconductor chip with this knob and measuring each time the voltage, Hall voltage. Okay, data is now over. Now just look. Hall voltage in millivolt. Then I converted in volt, dividing by 1000. Current in milliampere, and I converted in ampere, dividing by 1000. Field was in kilogauss, and field is constant because current was constant to electromagnet. How much field is? 180 Gauss. And thickness of the semiconductor sample in meter. So this is the value. Now you just apply a formula. Hall voltage, this one, multiplied by the thickness, this one, multiplied by 1 with 4 zeros. Why? The Gauss is converted into Tesla. Then dividing by current in ampere and also dividing by B in Gauss. So we have the value of Hall coefficient and units are meter cube per coulomb. Meter cube per coulomb. This is, RH. RH means Hall coefficient. Meter units, meter cube per coulomb. Now what is the advantage of the Hall coefficient? You can have an idea that your semiconductor or N-type semiconductor or P-type semiconductor, how much charge gauge density is available for the conduction. Charge density means charge per unit volume. How? Very simple. You can have the value of charge density by taking the reciprocal of Hall coefficient multiplying by the charge of the electron. Then this will give you the number density. Keep in mind, if the semiconductor chip is pure, then it will have somewhat less number density. But if it is N-type, then it will have more number density. So you just calculate, because the sample which we were using it was of n-type semiconductor. So mention what is the number density, charge density of n-type semiconductor. Thank you.